Hello everybody, welcome to Unit 6, where we are going to be talking about exponential functions. Today's lesson is key features of exponential functions. We're going to be going over graphs, and today we're going to recognize key features of graphs of exponential functions. We're going to perform transformations to exponential functions. We're going to identify exponential growth and decay rates, and then we're going to use exponential growth and decay to solve real-world problems. Alright, so let's jump into it. So first of all, key features of graphs. Let's talk about the function f of x equals a times b of x. So let's go ahead and go to Desmos. Now, if we just look at the graph here, kind of just ignore this for a second. If we look at the graph of an exponential function, what we'll notice is that we start off at some point, right? In this case, if we really zoom in, you'll notice that this will never actually get to 0, right? If we look at the y value, do you see how we're approaching 0, but we never get there, right? So that's one key feature of this kind of graph. Another key feature of this kind of graph is that we'll go off forever, right? We will eventually cover every x value, but you notice how it's increasing. The increase is increasing itself, right? So this is getting dramatically, the y values are getting dramatically, raising dramatically faster than the x values are. All right, and then we'll go over more specifics as to what this is, but this is what the function looks like. And remember, this is the base function would be a times b of x. In other words, our x value is actually the exponent of our function. All right, so let's go over a few rules in regards to our new graph here. First of all, a cannot equal 0, right? And let's go ahead and pull this back up, and I'll show you what happens if a equals 0. Right, so if I take this a value and I drop it to 0, you notice it just creates a line, right? This line here. And the reason for that is if we think about the math behind it, right? If a is 0 and we plug in a, then 0 times b of x is still going to be 0. So in other words, this whole graph is nothing but the line y equals 0, and that's because, well, zeros just kind of negate a lot of things, right? Especially in multiplication. All right. So now let's look at if b is less than 0. In other words, if we take this b value and we drop it here, you notice how it disappears when we get negative? Like here you can see the line's green down here, right? But if we go negative, it just disappears altogether. And the reason why is because the graph becomes imaginary, right? Well, it becomes complex, but for the sake of it, right, there are imaginary numbers, so it can't appear on this graph. And when we get into logarithms, it'll make a little bit more sense why those numbers are imaginary. But yeah, so we'll go over that here in a second, in future lessons. All right, the last rule is that b cannot equal 1, okay? And I'll show you what happens if b equals 1, just to give you, right? You notice here we still have a line, and the reason why b cannot equal 1 is because we gotta change a back to 1 here. Okay. And the reason why b cannot equal 1 is because 1 to any power is still just 1. Right, so in other words, it's not actually anymore it's no longer a exponential function. It's just a linear function, right? Because this whole 1 to the x is going to go away, right? In other words, if we do a times 1 to the x, it's always going to equal a, right? So if we look back at this, right? If we look at here, we have a equals 1. Our graph is 1 the entire time, right? If we change our a to 4.2, our graph is 4.2 the entire time. Right, and that makes sense just mathematically. All right, let's set this back to 1, and let's make our b 2. That way we have a real graph again. Okay. And remember, b can be it doesn't have to be 2, right? Like it could be 1.6, 1. It just can't be 1, right? It can actually even be between 0 and 1, right? It can be these kind of numbers, but we'll go over that later. All right, let's just set it to 2 for now, just as a kind of an arbitrary point. All right, so here's an important note, right? Because the y-intercept is where x equals 0, right? So here is where x equals 0, y equals 1, right? This is what a y-intercept is. So because the y-intercept is where x equals 0, if we look back at our original function up here, right? B to the 0, right? If we take this b to the 0, this whole b to the thing, right? That would all equal 1, right? And a times b to the 0 equals a, as we just talked about, right? Like right here. Which means that whatever our y-intercept is actually just whatever a is, right? So if we go back to our original function here, you'll notice that as I increase a, let's make a 4. Oh, what's our y-intercept? Oh my gosh, it's 4, right? And that's because essentially at b to the 0, this equals 1. So a, which would be 4 in this case, times 1 is just 4. So the y-intercept at x equals 0 is just 4. That makes sense, right? So in other words, the main takeaway of all that, I know that was a lot of mathematical speaking, but the idea is that whatever a is, that's what our y-intercept will also be. All right. So when we look at the function f of x equals 2 to the x, right? This is the same thing as 1 times 2 to the x, so our y-intercept is going to be 1. Don't mistake this and say our y-intercept is 2, right? 2x is the parent function. We're multiplying that parent function by 1. Does that make sense? So that's the 2 is going to be more of the rate at which it increases. The 1 is going to be the y-intercept in that case. Okay? So I put that in there just to kind of show you that this isn't a y-intercept of 2, it's a y-intercept of 1, and that's why when you look at the graph with all the things that we just did, right, if I put a back to 1 here, which is what we had in that problem, right, this is what we get, right? And in fact, like if real quick, if you just wanted to do like y equals 2 to the x, it's the same graph, right? Just to kind of show you, right, if I toggle these on and off, we get the same graph. Green, right? Okay. Cool. All right, so a few distinct features, right? When we talk about key features, we're talking about domain, range, asymptote, y-intercept, those sorts of things. We determined the y-intercept was 1. The domain, which is our set of x values, is going to go on forever, right? I know it looks like it may taper off at some point, but it literally just goes on forever. It just takes forever to get there because it's exponential, right? But it will be all real numbers. So the domain, all x's are possible. The range, like I said, for range, it's never going to go below 0. So if we take this graph, we go all the way over here, right? Eventually it does say 0 because it's tired of rounding it, but it will never actually hit 0, right? This is actually, it's similar to like the function y 1 over x, right? It'll never hit 0. All right. And then, so in other words, our range is y such that y is greater than 0. And then our asymptote is just the x-axis where y equals 0. All right, and this will, of course, change based on different transformations we do. All right, and then speaking of transformations, let's go ahead and look at our transformation formula here. And this will be, what, the 5th or 6th time this year that we're doing transformations, so should be pretty well acquainted with it, but let's go ahead and just take a look, okay? Now, a, of course, is going to be our vertical stretch, and if a is negative, it reflects over the x-axis. So if a is less than 0, it reflects over the x-axis, right? B to the x would be our parent function, and then you'll have minus h. So in other words, if the exponent is x minus h, the h is a horizontal shift left and right, and I'm going to show you how that works here in a second. I'm just kind of going over this pretty quickly here. And then the k is going to be the vertical shift up and down, all right? So let's go ahead and go to a graph, and let's take our function here, right? This is our green guy here is our function, and what we're going to do is we're just going to play around with some stuff, okay? So remember we said that a is going to stretch our vertically stretch our thing faster, and it's also going to reflect over the x-axis. So in other words, as a increases, do you see how it stretches faster, right? And by stretch faster, I mean like, okay, let's make a 1, and let's pick a random x value. So let's pick x value here. Let's say, what is this, 1, 2, 3? Let's pick 3. At 3, it's 8, right? So if I increase this a to 3, and now I look for 3, well, oh, it's up there, isn't it? Let's see. 3 is now 24, right? So a is increasing the rate at which the graph increases, right? It's our vertical stretch. Okay, and then if a was to ever become negative, right, it would flip it over the axis, right? As you can see, it gets more negative and stretchy, right? And then if it's ever between 0 and 1, it's actually like a shrink, right? So normally, like I said, if we have it at 1, it's good. This is our normal graph, right? Our normal function. If we have it at like 0.5, you notice it's going to go up less quickly, right? So remember at 1, 3 was 8. Now 3 is 4. So it's going up half as fast, right? At least at that point. It'll go half as fast, but at an exponential pace as it goes up. Okay, so that's A. Okay, we flipped it, we increased it, we decreased it, right? That's everything that A can do. All right, so H is our horizontal shift. It shifts it to the left and the right. And for this, I'm going to back out a lot because it looks kind of weird if it's up close. It kind of looks like it's doing different stuff. Let's go ahead and reset A to 1, and let's just watch what the H does, okay? As H becomes more and more positive, it shifts to the left, right? This is 10, and if we looked at the graph, you'd see it shifted 10 to the left. If we shift to the negative, it'll go up to 10, and it'll shift 10 to the right. All right? And usually a good way to do this is just kind of look at the intercept, right? In other words, the intercept was supposed to be at 1, right? Remember how we determined that? Well, now where it would have crossed, right, would have been like here. Here, let's think of it this way, right? The intercept, if I move this back to, let's move this back to 0, right? If we look at it here, the intercept is 0, 1, right? So it's at 1 when x is 0. And if we shift the h, let's go -10. Well, when we're at 1, now we're at 10, right? So we shifted it 10 to the right. Does that make sense? Okay. So now let's go ahead and look at k. And k is kind of the same idea, right? As always, it shifts it. It's attached to the end here. It shifts it up if it's positive. It shifts it down if it's negative. Let's put our h back. And let's make k. So if k goes up, right, we can do the same thing. So let's look at, we have, right, 0, 1. So now if we shift this up 10, right, what'll the number be? Well, we get 11, right? So when we shift it to the right, we get 10 because it was already at 0. And when we shift it up, right? So in other words, if we shift this up and to the right, let's go to the right, right? Then the point that we had before is now going to be 10, 11, right? Because it was 0, 1, right? So we shifted it up and to the right, both 10. Okay, cool. So note a negative x, right? So in other words, if this x here was like negative, if it was b to the negative x, a negative x will reflect over the y-axis at a rate inversely to b, okay? And so just to kind of show you this real quick, right? So this is, let me put my h and k back. If I have b as 2, right? B can do this, right? And it'll increase the exponential, like it'll make it exponentially increase, right? Kind of like A does. But you'll notice that, okay, when we get to a certain point, right? We said B can't equal negative, right? It can't be negative. But if B is between 0 and 1, do you see how it flips it over the x-axis here, or over the y-axis? And it actually becomes exponential decay, right? Which is what we're going to talk about a little bit later. But you'll notice that, like, if we had something that was worth this much here, as time goes on, it's going to become worth less and less and less, right? Whereas before, it would have been saying, oh, this is getting more and more valuable, right? So anytime B is between 0, well, greater than 0 and less than 1, right, we're going to have this exponential decay. And we'll go over that a little bit more later. But essentially, if the x is negative, what that's saying is the same thing as the b being a fraction. And it's going to be, the x being negative is going to be, the b is going to be inverse, and we'll talk about that here in a second. We'll go over that. All right. So let's go ahead and just do a couple problems. Let's do an easier one first. So identify transformations. If we have f of x equals -3 to the x minus 4, then essentially, well, first of all, we have to identify the parent function, right? In this case, f of x is 3x. So this part here is the parent function, and then the negative and the -4 are the transformations, right? So the transformations to our parent function, if a is -1, right, because this here is negative, so that's -1. It's the same as like -1 times 3, right? So if we have a of -1, it's going to be a reflection over the x-axis. And k, if it's -4, is going to shift it down 4. So what we should see, if we take our original function, right, let's make b 3, because that was what our original function would be. Right, okay. So if we have our original function here, now what it's saying is we have a of -1. So let's make a -1 and watch what happens. Okay, it flips it, which is what we said it was going to do. And then we also said that because k equals -4, it's going to shift it down. So let's make k -4. And that's what it did, right? We physically saw it go down, right? If it's up here and it goes down, k equals -4 is going to shift it down. All right, so we talked about it, and then we kind of just did an example just to show you. All right, now let's talk about that concept I kind of briefly mentioned earlier about the negative x, the negative exponent here, where x is negative. So if we have f of x equals 5 to the negative x, let me just show you that in graph form real quick. Let's reset these, because I'm going to use these to kind of prove my point here. We're going to go b equals, well, we'll just do 2. That's fine. Oh, no, it would be b equals 5. Well, no, here, we'll just stick at 2 for a second. Don't worry about this graph. I'm going to get rid of it. All right, so let's do 5 to the negative x. All right. So if we have 5 to the negative x, you notice how this looks like decay, right? And I'm telling you this negative x is the reason why it looks like decay. But what this is saying is that this 5 is saying that it's decaying 5 times as fast, right? That's kind of the way of looking at it. If I just had, let's do 2 to the negative x, right? Just to show you that it's increasing here, right? So, whoop, let me do that. 2 to the negative x, right? Do you see how like this one is clearly dropping faster? Like this one is taking its time to drop. This one's dropping like immediately, right? So the 5 is increasing the rate at which it's decaying. Now, the rate at which it's decaying is actually interesting because this is a 5, right? If we're multiplying the decay by 5, that's the same thing as like dividing the decay by 0.2, right? It's an inverse relationship. So if I take this b, right, and I lower it to 0.2, and then I turn this graph on, watch what happens, right? Oh, we need to make a 0 or 1 again. Isn't this interesting? What? Watch. Click this off, it becomes green. These are the same graph, right? Purple, green, right? So in other words, if b is 0.2, right? In other words, if this base is 0.2 to the positive x, it's the same thing as 5 to the negative x. Okay. Now that's a little bit tricky, all right? And it's not going to come up so much, but I just wanted to make sure that you understand like what this 5 is doing to this negative x, and that the negative x is decay in the same way that a fraction is decay if b is a fraction. Okay. All right. Like I said, it's kind of complicated. I just thought that was a really cool relationship, so I thought you'd want to see it. So went ahead and showed you that as well. All right. Exponential growth and decay. So now, just like before, right, this is exponential decay. This is exponential growth, right? If this is, if b equals 0.2, right, it'd be, so you can see it, right? You can see how like this is growth, this is decay, right? All right, that's kind of the idea. So let's go ahead and go over our basic formulas for these, and these are going to get a little bit more complicated in the next lesson. But for now, let's just stick to these because these will kind of help you understand what this is. So if we have a of t equals a times the quantity 1 plus r all to the t power, this is growth, right? And the reason why it's growth is because this is 1 plus r. And then if we have the same formula, but instead we have 1 minus r, right, this is going to be decay. All right, and when we do, we're going to do a couple of examples here, and I'll show you like when we plug these in why it's growth and decay. All right, but here's what these numbers mean, right? A of t is going to be our final total, right? Imagine if you're, in a mechanic shop and they're saying after X hours the total cost, right? Y is usually our total cost. It's the same thing here. Our A of t is our total, our whatever our total is based on the problem. A is going to be like our initial value, right? This is our y-intercept of other problems, if you want to look at it that way. But in this case, it's multiplicative. But this is our initial amount. So like if we have a population and we're increasing that population over time, our initial population is going to be A, and then A of t would be our population after so many years or whatever, right? T is going to be the number of increases or decreases. So in other words, if we're looking at a population increase, which we're going to do in the next problem, if we're going from, 2000 to 2010, and we're increasing at the same rate every year, or we're increasing by the same exponential rate every year, then we're going to have 10 instances of that change, right? So t would equal 10 in that case, because it's going from 2000 to 2010. Okay, so this is important, right? Note that 1 plus r and 1 minus r is the total rate, right? And r is just the change of the rate. In other words, if r was 0 here, right? Let's say it's not positive or negative, it's just 0. this isn't even going to be an exponential function anymore, right? It's just going to be a line. There's going to be no change. In other words, if my car is worth $4,000 and the change on the car is 0, it's going to be worth $4,000 forever, right? But if I say it increases by 10% each year or it decreases by 10% each year, that's when that R is going to come into play, right? It's going to affect the 100% value, right? So in other words, if it was 100% initially, if it's now an extra 10%, it's going to be 1 plus 0.1, right? If it was lower, right, if it went down by 10% each year, now it's going to be 1 minus 0.1, and you're only going to get 90% of the value, which makes sense. All right, so let's just do a couple problems. I think it'll make more sense of everything over here. All right, so exponential growth. The population of a large city was about 4.6 million in the year 2020 and grew at a rate of 1.3% for the next 4 years. What exponential function models the population of the city over time? What will the population be in 2050? All right, well, let's look at our exponential growth and decay formulas here. So let's go ahead, let's just write this down, all right? And then we can kind of get back to it. So we know that A of t equals A times the quantity 1 plus R to the t. All right, and this is growth, right? So it says that we're growing at a rate, right? So we know that we're going to use the growth function. We can move this back. All right, so if we're growing at a rate of 1.3% for the next 4 years, the 1.3 is going to be our R, right? And the 4.6 is going to be the population at 2020. So what this is going to do is we don't know A of t yet, right? We don't know A of t, that's fine. But this is going to equal 4.6 million. We're just going to put 4.6 now and then know that our population is in the millions, right? So 4.6 million times, and here this is going to be 1 plus 1.3%, right? 1.3% is the same as, right? Is 0.013, right? And then all of that to the t. So we can just add these together, and what we'll get is A of t equals 4.6 times 1.013 to the t. Right? Okay, so this is our rate, right? We don't know the final total because the final total is going to be based on how many years in the future we're looking, right? Okay, but now let's go ahead and look at this. So what exponential function models the city over time? Well, that's this. That's what we just found. What will be the population in 2050? Well, 2050 from 2020 is 30 years in the future, right? So we're going to have 30 instances of this growth. So what we're going to have is A of t, what is the final population? Well, that's the thing we don't know, right? Equals 4.6 times 1.013. And we're going to raise this to, well, what is t? T is the number of increases, right? So we went from 20 to 50. T is going to be 30, right? So we're raising all of this to the 30th power, all right? Now all you have to do is plug this into your calculator, right? Went ahead and save you the trouble here. This is going to equal approximately 6.78, right? So what this is saying is that in 2050, right, in 2050, the population will be 6.78 million, right? In other words, we increased by, what, 2.18 million people over the course of 50 years? All right, and you notice the rate wasn't that the rate wasn't that crazy, right? So that kind of makes sense. All right, cool. So that's exponential growth, right? We're literally we have our formula. We're using the formula we're just kind of plugging in the stuff where it goes into the formula, solving for what we need. All right, exponential decay. The value of a car is represented by the function below, which is down here, in thousands of dollars. X years after it was purchased. So in other words, the total cost will be this X years after it was purchased, okay? Does the function represent exponential growth or decay? What was the initial value of the car? What is the change in rate? And when will the value of the car be about 5,000? Okay, so anytime you have a problem like this, it's important to draw a picture. And I've explained before, graphs are the pictures of algebra 2. So let's go ahead and just graph our thing. So we have 24 times 0.8x, 0.8 to the x. So here's our graph, right? This graph is going to answer a lot of questions for us. It just is. So let's look back at it. We have, does the function represent exponential growth or decay? Well, what does this look like? It's decay, right? It's getting smaller and smaller and smaller. So yeah, it's decay, right? And let's explain why for a second, okay? What is the initial value of the car? Well, the initial value of the car is going to be what it is the year that we purchased it, right? So at year 0, in other words, if year 0 is where x equals 0, we know the car is worth, let's get to 0 here, 24. So if it's 24, the initial value of the car initial value is 24,000. Okay, nice. So we knew the car is initially worth 24 grand. All right, what was the initial value of the car? What is the change in rate? Now, here's where this actually becomes kind of interesting, right? We know that it's decay, but exactly how much is the decay? Well, let's go back over here, right? Remember how when I was telling you about growth and decay, I said that 1 plus r is the total rate and that r is just the change, right? In other words, this 8, we got this 0.8, if you want to like think of it like this, right? This is, if you want to look at this formula like the other one, right? We could say this is like f of x equals 24 times, right? This 0.8 would have had to have been 1 minus 0.2, right? That's how we would get 0.8. Does that make sense? And I'm going to explain this in much more simple terms, but this is the mathematical way of looking at it, right? So 0.2 is the rate of decrease, right? What is the change in rate? The change of rate is negative 0.2, which is why it's a decay, right? Because we're going down this much every time. Now, the other way to look at it is, okay, if our total was 100%, right? If 100% means it's maintaining its value perfectly every time, right? And now it's at 80%, right? If we went down to 80%, that's actually a decrease of 20%, right? It's a decrease of 20%. In other words, it's the same thing as this, right? 0.2, 20%. So you can look at it however you want to. What is the change in the rate? 20%. 0.2. Negative 0.2, right? All right. What will the value of the car be in when will the value of the car be about $5,000? Now, you guys don't know. I mean, I could just show you this, right? So we have f of x equals 24 times, and we determined that this was 0.8 to the x, right? So we don't know, in this case, the x is t, right? It's the same concept, but you guys don't 100% know how to solve for this yet, right? So that's fine. We're going to be talking about logarithms later in this unit, but what we can do is we can just look at the graph, right? In other words, when will the car be about 5 grand? Well, if we know that x is the number of years and y is the total value, we can say like, okay, well, when is y 5 grand? In other words, 5, right? So if we look at 5, where is y 5? Somewhere around here. I mean, you could tell it's close to 7 years, right? It's very, very close to 7 years. So that's kind of a good way of looking at the question, right? When will the value of the car be about 5 grand? Well, the car will be about 5 grand at 7 years. Like I said, we'll go over the math on how to solve for x in these cases, right? Because right now we can use logs to figure that stuff out, logarithms. But for now, we can just look at a graph and it will tell us the answer. All right, and that's it. So first of all, we did exponential growth, right? And then we did exponential decay. And you'll notice that they're very, very similar. The only difference is that one is adding the rate to 1 and one is subtracting the rate from 1. All right, so what did we do? We started off by talking about the graph, right? The very basic graph here. We figured out that the y-intercept is nothing but a, right? It's very, very similar. We identified range, domain, and asymptote and everything here. Then we talked about transforming functions, where a is the vertical stretch or the reflection, h is the horizontal shift, and k is the vertical shift. And then we talked a little bit about what happens when x is negative, in that it's essentially a form of decay, right? Then what we did is we talked about what growth and decay look like as far as their formulas go. We did a problem with exponential growth, where we took the population and increased it over 30 years. And then we did exponential decay, where we basically looked at a graph, and we learned a lot just from looking at that graph. All right, awesome. Well, that's the end of this video. I will see you in the next one, where we're going to talk a little bit more about what we do with exponential functions. Have a good one.